here, so ignore me. Okay, a few people had questions on this worksheet called the Empirical Formula Worksheet. So we're going to go over, I'm going to just jump right into this. I find with empirical formula, this type of problem, it's better to just kind of learn the method. And then if you have questions after that, then come in and ask them. And I think you'll find out the reason you're doing it this way pretty quickly if you learn the method. Okay, so the first thing that we need to do is just define what an empirical formula is. There's two different ideas here. First is what's called a molecular formula. That would have been so nice. Okay. Okay. I'll try one more time. Let's start. Like totally, pieces on me. I guess I just have to edit it afterward. That's the annoying thing. All right. I never did a recording on this, so. All right. So we're going to be going over the empirical formula worksheet, which most people, I think, every single person that completed this had questions. I don't think this isn't one where, so it tells me that I definitely need to make a video. This won't be I need to make one of the Edpuzzle videos. So it's kind of a gap in the Edpuzzle videos. I think I got a little overwhelmed by this point when I started doing those. So there's two things that first of all we need to be aware of. That's two terms. First of all, we have molecular formula. Okay, I need to fix my calibration. Give me a second, I'll pause this. Let's start that again. All right, so there's the molecular formula, and then there's what's called the empirical formula. Oh, that's so stupid. That noise is not going to make it. Okay, formula. All right, so the difference between these two, I'm just going to keep this really simple, and then we're just going to get right into how to do these problems. Okay, but just so that you're aware, the molecular formula might be something like, for a certain molecule, it would be called, its name is ethane. It would be C2H6. Okay, so that's the molecular formula. That actually describes the specific molecule. And just so you know what that would look like, well, I won't draw it right now. We'll hold off on that. But you could draw that out, and I could show you on the board. It has a carbon with 3 H's coming off of it, bound to another carbon with 3 H's coming off of it. Okay, and so that's the actual formula for that molecule. But the empirical formula is essentially the molecular formula, but in lowest terms. Okay, so C2H6, Nick, what would that become in lowest terms? If you were to reduce it like you're reducing a fraction. So what number could be, what's that, CH?
Yeah, it's 3.
3, exactly. So you could divide each of these by, you could divide the 2 and the 6 each by 2, and it would come out to be CH3. Okay, so the empirical formula for this molecule would be CH3. So the empirical formula is only concerned about the ratios of the different atoms, whereas the molecular formula is the actual molecule, describing how many atoms you have of each type of atom on that molecule. Okay, so that's just something to be clear about. When we're doing percent composition, initially we really are only calculating the empirical formula. And then if we happen to know the molecular weight of the molecule, then we can figure out the molecular formula. Okay, and we'll go through and we'll show you how this works. Okay, so the first problem, we'll do 3 problems, and we're going to try to select 3 problems that give you a variety of the types of issues you face, and then from there, you'll be able to figure out, I think, most of the rest of the problems. Liz, would you mind closing the door? We're getting like a little bit of a whirlwind there. Okay, so first of all, what is the empirical formula for a compound which contains 0.0134 grams of iron, 0.0769 grams of sulfur, and 0.0115 grams of oxygen? Here's how I recommend you do this. Okay, so stick with the method, and I'm not going to explain a lot about why we're doing it this way initially, but I think as you do it, you'll see why. It'll kind of become obvious. Your goal, first of all, is to go from whatever you're given to get to how many moles you have of each of those substances. Okay? So the first step here is you just write over here to the side 0 0.0134 grams of iron. Okay. We do the same thing with the sulfur, 0.00769 grams of sulfur and 0.0115 grams of oxygen. Okay, so, Zayla, how do I convert these to moles?
The dimensional analysis.
Okay, and what do I use for my conversion factor, Nick? It's the same answer. Almost every time we talk about moles, we always do what? We calculate the molar mass. It's always, whenever we're like, I don't know what to do, it's probably molar mass. Okay. So in the case of iron, Nick, can you tell me the molar mass of iron? That's a good place to look. I look at element number 26. What's that?
55.85.
55.85? Okay, so we got 55.85 grams on the bottom equals 1 mole. Okay, because we know that iron is 55.85 grams per mole. Okay, so what we're saying there is we're saying that 55.85 grams is equal to 1 mole, and therefore in a conversion factor we can have that flipped upside down or right side up. It doesn't matter because both are equal to the other. Okay. And to be really clear here, this only is in the case of iron. Okay, so then we cancel this out. Okay, we cancel this out, and then we're going to get a number here. Can anybody do this calculation? Does anybody have a calculator? You have a calculator?
Oh, yeah.
Okay, maybe pull that calculator out, Nick. I'm going to pull one out as well.
What do you want me to do? What? What am I multiplying?
Yeah, just multiply. We're going to just take. We're going to do this exact problem here. We've got 0.0134 divided by 55.85. That's the number there. Let me see.
I got it.
What is it?
0.002324.
Keep going. Give me some more digits. 2.
24. That's missing.
Oh, more digits. Yeah, give me guys.
Okay. T399.
Okay, good. That looks like good. We're going to stick with 4 digits because we've got 4 digits in some of these. When you're doing your intermediate calculations, like when you don't get to the answer, it's okay to keep extra digits. And then at the end, you can do your rounding based on how many significant figures you have. Okay, the next one, sulfur. Could you give me the molar mass of sulfur? Zayla. 32.07. So we just put 32.07 grams per 1 mole. Okay, and this is, and by the way, this is moles of Fe. We got to be really clear that in this sample, you can have this many moles of Fe. Now the next one is going to be moles of sulfur. So who could do that? Probably.
0.002397.
So pretty similar number. Moles of sulfur. And then this last one is oxygen. I know that one, so we're going to say 16.00 grams per 1 mole. And this is, of course, oxygen. We got to kind of clarify what we're referring to. And so now, if we can do one more math problem there. Nick, you got that calculation there?
No, I was writing down.
Okay.
0.00071187.
Moles of oxygen. Okay, guys, so here's the key, right? So we have a molecule, or a compound, that includes iron, sulfur, and oxygen, okay? Now, we just figured out how many moles we have of each of these. So this will tell us the ratio of the moles will also be the ratio of the atoms, okay? And this is the idea that says, okay, if you have 2 dozen of sprinkle donuts and 1 dozen of glazed donuts, then we know the ratio is 1 to 2. It's the 1 to 2 for donuts. It's also 1 to 2 for dozen. Same thing here. The ratio here, whatever this ratio is going to be the same for moles. It's going to be the same for atoms. So we're trying to figure out the ratio because we're trying to figure out the compound formula. Okay. So now, the only problem is that when it comes to ratios, not a problem, but by convention, when it comes to ratios, when it comes to the ratios in the formula, we don't do, as you guys know, we don't say Fe 0.25 and what were the other ones? Sulfur, 1.23. Okay, we don't do that. We have instead whole numbers. Okay, when we're talking about the ratio in an equation, we use whole numbers, okay, which makes sense because they refer to atoms, and it's kind of hard to imagine a half an atom or something like that. So the question is, these ratios are already correct. It's 0.0002399 to 0.0002397 to 0.0007187. Okay, but they're not whole numbers. So the question is, how do we get those into whole numbers? Here's the method. Okay, what are we going to say? That would put it in whole numbers. Well, eventually, you'd have to multiply by, what, like 10,000 or something like that? But I'll show you another way. Okay, so the key is, guys, when it comes to ratios, as long as you do the same thing to every one, when it comes to either multiplication or division, as long as you do the same thing to every one, you're going to stay in the same ratios. That's not true of addition, but we're not going to do that anyway. Okay, so look at this, guys. All we do is this. Find the one that has the smallest number of moles and divide everything else by that number. Okay, so Nick, which one is the smallest here? Is it the sulfur, the iron, or the oxygen?
Sulfur.
Sulfur. Good job. Okay, so we're going to divide this by 0.002397. Divide this by 0.000397. Divide this by 0.000397. And so we already know, obviously, this one is going to come out to be what? This one right here. 1, clearly. Okay, so I'm going to put a 1 in here. Okay. Now the one on top of it, you can already tell. You can do the division problem, but in fact, do it just to confirm. You can essentially round it to 1. Okay. But try the division problem just to make sure we're good. Nick, can you do the last one?
Yeah.
What'd you get there?
0.000000.
Which one did you do? Did you do the first one? Okay, so you must have put less zeros in one of those. Because it should come out to be very close to 1. You've got 0.0002399 divided by 0.0002397. It should come out to be like 1.01 or something like that, or 1.001. Kaya, what are you working on back there? Kaya.
Oh, yeah, okay. I messed up. It's 1.0008334.
Okay, so let me just show you that number, 1.0008. Okay, so guys, when it comes to this step, when you're just trying to figure out the whole number ratios of those atoms, okay, if it's within 5% of being a whole number, just round it to a number, or round it to the whole number. So in other words, if it is 1.05 or 0.95 or anything in between, you can just round it to 1. Okay? So this one obviously is way less than 5%. So this one we can just round to a 1. Now, Nick, did you do this last one?
Yeah.
What did you get?
I didn't get close to 1 though. Does that mean I'm wrong?
Did you get close to a whole number?
Yeah.
What was the whole number?
3.
So it's very close to 3.
Yeah.
That's probably correct. What's the number?
Oh, at 2.998.
So 2.998. This fits that standard where it's within 5% of being 3. So you can put right here a 3 for that. Okay? So now we have a ratio in whole numbers. It's 1 to 1 to 3. So now we can figure out our empirical formula, and it's going to be this. Okay, I know it's getting a little sloppy here, but it's going to be Fe, boy, that was not so good, SO3. Okay, did you guys see that? Because iron here, that was the first one we calculated. That, the ratio of the iron is 1. To the ratio of the sulfur is 1. To the ratio of the oxygen is 3. So then we put that into a formula, and it becomes just FeSO3, because when it doesn't have, when you don't put any subscript, that's the same as having a 1. Does that make sense, Zayla? Does that step make sense, how we got that formula?
Yeah.
Okay, Nick? Seems cool? Okay, awesome. All right, let's do the second one. We're going to do 2 more, okay? And I think once we do 2 more, then you'll figure out the second one is not too long, but there's one little difference there that you're going to want to notice, okay? So in this one, it's a little bit different because they don't give us the number of grams. All they give us is the percent composition. Now, something you have to be really clear about when they give you percent composition. They are not talking about the, this is really important, guys, so they're not talking about the percent of atoms of that type. Instead, they're talking about the percent of the entire mass of that substance, okay? So in other words, hydrogens have a lot smaller mass than oxygens, okay? So you might have more hydrogens than oxygens, but oxygens still might make up more of the mass, okay? So you could think about that as an elevator. They have these limits on the elevator, okay? If you have little kids there, even if you've got 5 of them, or one big person, okay, then they might make up more of the mass than the 5 little kids, okay? So you're looking at the percent mass. So here's the thing. When it says that the empirical formula for a compound contains 32.8% chromium and 67.2% chlorine, okay, if they do not give you a total mass for the substance, okay, here's what you want to do. You want to assume 100 grams, all right? So just assume there are 100 grams. Now, to be frank, you could assume whatever you want. You could assume there were 75 grams or 50 grams, because when it's percentages, when we're talking about percentages, it doesn't really matter how much of something you have in total, okay? What matters is, like, for example, if you had, what would be a good thing that has a ratio in it? If a pie, for example, was half raspberries and half, what else do you put? Like peaches or something like that. Half raspberries, half blackberries, okay? It doesn't matter if the pie is, so the ratio of blackberries to raspberries is 1 to 1, and even if the pie is 3 times as big, the ratio is still 1 to 1, okay? So it doesn't matter what you use, okay? But here's why it's helpful. If you assume 100 grams, then, Zayla, if I assume my total is 100 grams, how much chromium do I have in that sample? 32.8 what? Grams, exactly. So you saw why it's so simple, because she didn't have to pull out her calculator. She just realized that it's 32.8 grams. So we're going to say 32.8 grams of chromium. And Nick, how many grams of chlorine do I have?
67.2.
67.2 grams. Do you see why it's nice to assume 100 grams? Because if you would assumed 105 grams, then you had to pull out your calculator and start calculating. You don't have to calculate anything here. It makes it so simple. Okay, so now we need to do the same thing. We're going to make this part simple, guys, because you guys just did it. That's actually the big step on the second problem that I wanted to highlight. It's just the fact that you assume 100 grams. The rest of it is exactly the same as the last problem. Okay? All we do is we put the molar mass for chromium. Okay? And in this case, Zayla, what's chromium's molar mass? It's number 24 there. 52.00 grams for every 1 mole. Okay, very good. Nick, what's our molar mass for chlorine?
35.45.
35.45 grams for every 1 mole. Awesome. And now we need to just calculate that out. So this is actually a relatively easy one. So always when you do a calculation, have in your mind about what it is. So we know this is going to be over half, over 50, over 0.5, but less than 1. So maybe like 0.6 or so. 0.65. What did you get? 0.6269. All right, that's good. And that's going to be moles of, because of course grams cancels out. We're left with moles. Moles of chromium. And then what about the one down here? Zayla, did you get the second one by chance?
No.
You mind checking that one? Should be something close to 2, but not quite 2 is what I would say.
1.895.
Okay, 1.895 moles of chlorine. And then Nick, what should I do next? Now I know how many moles I have of each of these, but we know that in a empirical formula we need to use whole numbers. These are obviously not whole numbers. How do I get them to whole numbers? What should I do?
Divide them both by the least.
By the smallest number of moles. Good. Excellent. Way to remember the method. So we divide this one by 0.6269. Divide this one by 0.6269. And remember that if you divide two numbers in a ratio by the same number, then it still holds the ratio to be true. It doesn't change the ratio. Okay, so if you have a ratio of 1 to 2, if you multiply both by 2, then it becomes 2 to 4, which is the same ratio. One's half of the other. Okay, or divide both. It doesn't matter. They're going to come out the same. Okay, Nick, what did you get? Obviously, this one is going to be a 1, correct?
I got 3.
About 3. Okay, very good. So there you go. So we just figured out that our formula then, Zayla, what's our final formula?
It's we have 1 chromium.
Okay.
And 3, 4.
So CrCl3, right?
Yep.
Okay, my handwriting's sloppy here because of the calibration's off again. Okay, so CrCl3. Excellent. Nicely done, you guys. Whoa, I thought that would stay on the thing.
Can I get a picture of it?
Sure, take a picture of it.
It's not on paper.
She doesn't have the assignment there. Okay, let me pause this for 1 second here. We're going to do one more problem, and it'll be the final problem. Let's try number 4. I think this one will help you understand this last point, I believe. I'm not sure. I got to see how it comes out. Okay, so first of all, the empirical formula for a compound which contains 67.1% zinc and the rest is oxygen. So they do a lot of these that are kind of, simple. It's just, they're just kind of putting little tiny math twists on there. You got that down. You got it. You got it, man. You're set. Okay. So 67.1% zinc and the rest is oxygen. Nick, how much should I assume we have in total?
100 grams.
100 grams. All right. Let's assume 100 grams. We'll put assume 100 grams. Okay. I don't know why it's so fat on my writing, but oh well. Okay. So, Zayla, how much zinc do I have if I assume 100 grams?
67.1 grams.
Good. And Nick, how much oxygen do I have?
What's that? Minus 67.
32.9
Yeah,
sounds
got
pretty
it.
good.
Whoa, wait.
Did we just
It's 32.9.
Thank you, man. Thank you for coming through.
You guys just said 32.
Well, she actually said 32.9. That's good. Okay. So we've got, let's do some quick molar mass here. Nick, give me this molar mass of zinc.
Where is
Zinc would be number 30. Element number 30.
65.39.
Grams per 1 mole. Cancel. And then oxygen is 16.00 grams per 1 mole. Okay, so now we do some math there. So Nick, what does this come out to be? And the second one there, and Zayla, if you want to get the first one.
2.056.
What the? This is like somebody from the future.
The layout of how a network communicates with different devices.
It's not too exciting. I think it's some YouTube thing that was still running.
Wait, I
Okay,
thought I was
2.056.
I thought I was
Oh, sorry, I guess you're doing the other one. 2.056
okay.
moles of oxygen, and then Zayla, what do you got?
1.023.
1.023. Oh, this wasn't a good one. Okay, sorry guys, this did not show the example that I wanted it to. Maybe it's the next one we have to do. Okay, so 1.023 divided by 1.023. This is too obvious. This is obviously 1 to 2. You guys picked that up right off, obviously. So that would be.
I actually did not pick that up. Wait, were you looking
Oh.
for one where it's like 5%?
Yeah, I wanted something that is. No, I want something that has a 0.5 in the answer instead of coming out nice and clean like that. So I can show you what to do, and I think the next one does. And if it doesn't, then So this is going to be zinc, Cl, or which is no oxygen. Sorry, I got the wrong thing there. Zinc O2, ZnO2. So what's that actually called?
Zinc oxide.
Zinc oxide, and we could put a 4 in there because it's a transition metal. So zinc, Roman numeral 4, oxide.
Oh, I was joking.
Yes.
I didn't know that was.
It's a Z, okay, Haley.
It's a Z.
I see that as a
Sorry?
T.
Oh, you don't do number 5. Number 6, there's a copper sample at your station. So you just go into the lab and copper sample. That one you can't do in advance. Okay, guys. Yeah, number 5 looks a little more challenging. I think we can crank this out, though, pretty easily by analysis it finds that it contains.
Oh, heck, I wrote in number 3.
So, guys, yeah, this will be a good one. This will be our last one. Okay. So it doesn't really, to be honest with you, this is extra information. We don't even need this. Okay. All right. So we start off with 97.56 grams of carbon, 4.878 grams of hydrogen, 52.03 grams of oxygen, and 45.53 grams of nitrogen. Okay, so let's do this. Zayla, can you convert? How about you take care of carbon? Or your goal is to tell us how many moles we have.
Okay.
Okay, so you know what to do there, of course. We get our molar mass 12.01 grams per mole. Nick, I want you to take hydrogen. Let's switch off. So we've got Zayla, Nick. All right. Should I give you one, Kiara?
Hey, I
I can do the oxygen once I know how many
Okay.
thingies.
Kiara wants oxygen. 16 grams per mole. Okay. So hydrogen is going to be 1.01 grams per 1 mole. Oxygen is going to be...
That was 1.008.
Yeah, you can use that too if you want, Nick. I said two decimals you need to go to, but you can go to 3. I don't mind. That means you're just more precise than the average chem student. You know? What can we say? This is 14.01. You got yours?
Yeah.
Okay, so Zayla, what are you getting here?
8.123.
Moles of carbon.
Oh,
And
wait,
then-
I'm not done. I was running everything down.
And then the other one is 3.2518.
This one for oxygen.
Yeah.
3.2518 moles of oxygen. Okay, and then what do we have for hydrogen? Who's doing hydrogen? Okay. All right.
4.8.
4.8.
Yeah, 3.9.
Moles of hydrogen.
Oxygen is what again? Is it 3.5 what?
2518. Yes. And then what about nitrogen? Anybody help me out on that one?
3.498.
Well, sorry, my erasing. Let me erase that here. Yes. Okay. Here. Work on the copper one first.
Okay.
You've got 2 of you there. Okay. You're supposed to measure out the other ones,
Oh, okay.
but I don't think you're gonna get to that. Okay. So now, what do we do to finish this off, Zayla?
Now we divided everything by the smallest number.
Which is what?
Which is oxygen.
One of these two. They're both about the same. So 3.2498. Divide this by 3.2498. Divide this by 3.2498. And okay. Kiara, can you do this one? Zayla, can you do this one? Nick, can you do this one?
Oxygen.
Who else has got a calculator there?
Oh, I don't know.
You got oxygen, Nick.
Oh, I was making
Sophia, can you do one calculation for us? Oh wait, we know this is about 1, so you don't have to do this one. That's already 1.
That's
I
what
got
meant to say.
I got this one. I got this one. Okay, so this is 1. What do you get, Kiara?
She can't comprehend this.
I got 2.4995.
Okay, good. I'm glad we got that because you guys notice that 2.49. So guys, that is not close enough to. We cannot round this to 3 or 2. That would make zero
Which one
sense.
was I supposed to do?
You were supposed to do the second one, I think.
Like 5 again?
Yes. So did you guys notice that 2.49? Now you can round that to 2.5. Okay, because remember, if it's within a 5%, we can round it to 2.5, but we definitely can't round it to 3. That would absolutely make no sense. It's 50%. So we'll see what the other two are. This one's about 1. Thanks, Nick.
Wait, so if the answer is 2,
Okay.
for what?
Okay, we got one more here, guys, and then we're going to conclude this.
1.4 divided by 1.
So it's which one was this one?
Hydrogen.
1.49?
1.489.
1.489. Okay, so so I'm going to round this one to 1.5. Okay, because 1.489 it's within 5% of 1.5. We're going to round this one also to 2.5. Now, okay, guys. So what do we do with this? Okay, we are supposed to have whole numbers. Okay, how can we get these into whole numbers? Okay, those of you who are
Whoa.
done.
Multiply.
Multiply by what do you guys think? What do you guys think we should multiply by?
the lowest number.
1/2. Wait, no.
2 is a great idea. So here's what I recommend, guys. If you get numbers that are not whole numbers like this, start by trying 2, multiply everything by 2. If that doesn't get you to whole numbers, multiply everything by 3. If that doesn't get you to whole numbers, I would go back and check your math, right? Because usually we're not going to go over 3 multiples, okay? So times by 2, times by 2, times by 2, and make sure you multiply all of them by 2. If you multiply 1 by 2, you've got to multiply all of them by 2 to maintain the integrity of your ratio. And so, if we multiply this by 2, it becomes 5, this becomes 3, this becomes 2, and this becomes 2. We've just solved our problem. We have C5, H3, O2, N2. Boom, boom, that is it. So guys, that's essentially the theme. Everything else you can figure out as long as you just use those methods. If you're just given percentage, assume 100 grams, divide by the smallest number of moles, and then if your ratios are not whole numbers, multiply by 2, try multiplying by 3. If you're not there by 3, go back and check your math because I don't think we're going to have any that are more than 3 that you have to multiply by. Good?
You always have to multiply by 2. It's like 0.5.
Yeah, you can start picking up. It's 0.33, it's going to be 3. If it's 0.5, it's going to be 2. Sarah, you got it down?
Yeah.
Awesome. Kiara, you got it down?
Yeah.
All right, you ready for you're ready for next year. Sophia, you got it down, you know?
Yeah.
Okay, Nick, how you feeling?
Get it?
Bust that out
Can I have a copy for my
for
property?
participating in the studio audience.
Yeah.
All right.
Oh, you start recording. No, that's one thing.